This is tutorial 7, question number 2. And in this question, we have a 5-ton machine that has to be pulled up an incline of 1 in 14 on 2 steel skids measuring 1250 by 80 millimeters each at a velocity of 300 millimeters per second. First of all, calculate the pulling force required unlubricated if the friction coefficient between the skids and the platform is 0.35. So that is the mu value. So the pulling force is mu n, which is your frictional force resisting movement, plus mg sine theta, which is the component of the force of the mass that is pulling the machine down the slope. So mu is 0.35, and that is times 5,000 times 9.81 cos of 4.08 degrees plus 5,000 times 9.81 sine 4.08 degrees. Alright, theta is equal to arctan of 1 over 14, which is equal to 4.08 degrees. Alright, so our total force then works out to be 20613,86 newtons. So that's the frictional force to overcome friction on the surface plus the component of the force due to mass that is pulling it down the slope. So our second question is, what is the pulling force lubricated? And we have a film of 0.05 millimeters on the skids of grease acting as a lubricant. The dynamic viscosity of the grease equals 0.22 kilograms per meter second. So now we're going to compare the force required if you lubricate the skids. So that's number 2. Pulling force lubricated. The thickness is 0.05 millimeters of the grease. U is equal to 9.22 kilograms per meter second. That's dynamic viscosity. Alright, so our force lubricated is nu v over t times area plus mg sine theta. 0.22 times 0.3 over 0.05 times 10 to the minus 3 times 2 times 1.25 0.08, because there are 2 skids. And now we add the force due to gravity. 5,000 times 9.81 times the sine of 4.08 degrees. That gives us a force with lubricated skids of 3753.87 newtons, significantly lower than the 20,000 newtons unlubricated. That's only 3,000 newtons. Right, the third question is derive an equation from first principles for the torque required to overcome fluid friction on one flat side of a circular disc coated with lubricating layer of oil. Alright, so this would be similar to question 1. I'm not going to write out the full description. So we have torque is equal to force times radius. We have dt is mu omega r over t times 2 pi r dr times r. So that's our elemental strip, the torque on the elemental strip. So our torque is equal to 2 pi mu omega over t, the integral between r1 and r2 of r cubed dr, and therefore the torque is equal to pi mu omega over 2t r to the 4 between the limits of r1 and r2. And that is the end of the question.